Okay, here we are. By the way, you caught me off guard. You don't need this additional assumption that the polynomials f and g in the Chinese remainder theorem are non-constant. Actually, if f is constant, then the corresponding quotient ring is just the zero ring. So its dimension will be zero.
I'm sorry, if you're writing something, we can't see it. You aren't showing your screen.
Okay, let me show you. Do you see this now?
Yes,
yep.
We can see now.
Okay, I mean, if your polynomial f has 0 degree, then by definition, what is this set? Is the set of all polynomials with degree strictly smaller than 0. There is only one polynomial with this condition, the 0 polynomial. So if f and here, if f is constant, non-zero constant, then this ring will consist of the 0 element only. So it has dimension 0. So it's perfectly fine. So if f has dimension 0, then this quotient ring also has dimension 0. And it works perfectly fine. It's an unusual case, so that's why I don't want you to break your brains. So just forget, we will for simplicity assume that f and g are not constant, but even in case of the constant polynomials, it works fine. Is it clear?
Yep.
Okay, so let me stop the demonstration. I just want to switch the whiteboard for the seminar. Okay. And just 1 second. Yep. Okay, so our goal for today is really simple and straightforward. We need to learn how to compute some basic things with polynomials. We will be doing that. So first of all, I want to compute a greatest common divisor for a pair of polynomials. Let's discuss how to do this. And just in case, is there anyone who have never computed a greatest common divisor for polynomials? Okay, so let's start with this example. So we will deal with polynomials with real coefficients. Our f is x to the 4th plus 3. Oh, come on, I'm blind. 2x3 minus x cubed minus 4x minus 2. And g is equal, I'll take it from the sheet of paper, x4 plus x3 minus x2, by the way, it's x2 here, minus x2 minus 2x minus 2. Okay, these are two polynomials, f and g. I want to compute a greatest common divisor of these polynomials. And actually, if we compute a greatest common divisor with the leading coefficient 1, which is monic greatest common divisor, we will get a unique result. So how do we compute? So first of all, we want to compute this f g. First of all, we want to divide f by g with remainder. F equals, well, it's clear that, well, let me write it like this. So we want to find an element here and the remainder here. So could you tell me what should I write here and here? What is the quotient?
Q.
Again?
Just one.
1, yes, it's just 1. And the remainder will be x cubed minus 2x. So if you subtract g from f, which means that you take here q to be 1, so the difference will be exactly this expression. So this is your q1, so I will use a different color, q1, and this is your r1. Now you want to shift g here and r1 here, so you want to divide g by r1 with the remainder. So let's try to compute what will be here. Yes, and g is here.
X plus 1.
Okay. X plus 1.
X squared minus 2.
Okay, x squared minus 2, exactly. So this is your q2, and this is your r2. Now we want to shift this again, and you will get r1 equals something, r2 plus the remainder. So I want you to compute these things.
Well, just x plus 0.
Yes, here x and here is 0. So you see, you will get 0 here. So it means that we should stop. So let me show you the whole computation. Just in case, are there any questions until right now? Okay. So, and what is the greatest common divisor?
X squared minus 2.
Yes. So if this guy is 0, then the greatest common divisor is the remainder on the previous step. So this is your GCD, which is this. Okay, so the GCD is computed. So GCD of f and g is x squared minus 2. So now let's discuss how to get the representation of the GCD in terms of UF plus VG. Do you have any idea how to do this?
Well, maybe we should substitute f and g with the actual polynomials and multiply it by something.
Well, actually, we should go in these equalities from bottom to up. You see, you know that R2 is equal to G minus X plus 1 R1. This is your second equation. I just move this expression to the left. Okay? And then from the first expression, you see that R1 is equal to F minus G. So you can substitute R1 here, and you will get the required expression for the GCD. So your GCD, which is R2, is equal to G minus X plus 1 times R1, but R1 is F minus G. So at the end, you will get X plus 2 times G minus X plus 1 times F. And this is the result. So this is your U, and this is your V. Is it clear? Are there any questions? So you see what you do here, you just substitute R1 here. So R1 in the first line, R1 is a combination of F and G. So if you substitute it here, instead of R1 here, you will have a combination of F and G. You move it to the left, then R2 is a combination of F and G, and you can substitute it in to the next line. Well, I suppose in case this is not 0, you just proceed in a similar way. So you just express the remainder on the kth step as a linear combination of f and g and substitute into the next line, and then you express the remainder of the next line as the linear combination of f and g. So here you need two substitutions. Well, all these substitutions are represented by the blue lines. So here, well, you just substitute g instead of f, but here you substitute instead of r, you substitute this difference. And if you need to proceed in the third line, you just replace r1 by the corresponding expression, and you replace r2 by the corresponding expression, and you will get the expression for r3. Well, if it were not 0. Are there any questions? Okay, then let's try to repeat this, but in case of more interesting field. Suppose now we deal with the field z2 of x, and f is equal to x cubed plus x, and g equals x cubed plus 1. Let's try to divide f by g with the remainder. What should I write here? Is it clear how to divide the polynomials here in this specific case?
Yeah, it's 1 plus
Well, it's 1
x
times
minus
g
1,
plus x minus 1, yeah.
x minus 1.
X plus 1.
Yeah.
There is no difference between minus 1 and plus 1
Okay.
Ah, it's the 2.
because it's z2. It consists of 0 and 1, and minus 1 equals 1 in this case. Okay, so this is your Q1, this is your R1. Now you want to compute G equals R1. What do we have here?
So x
Well, 0
cubed.
times r1.
What again?
Well,
No, why
I
0?
think here is
Squared plus x
No.
plus
ah,
1.
it's g. But,
Squared.
X squared plus
Sorry?
x plus 1.
Squared.
Like неполный квадрат.
Yeah. The formula.
So
Yeah,
it's square plus x plus 1 will be the quotient, and the remainder is 0.
Yep.
Just in case, do you need me to compute this explicitly? Is there anyone who doesn't understand how we get these polynomials, at least one of them? And should I explain how to divide? Okay, but one, I just want to add one remark. When you divide in Z2, so for example, you want to divide x cubed plus 1 by x plus 1, what would you do? You do exactly the same algorithm as with usual polynomials. You multiply by x squared, and you will get x cubed plus x squared, and then you subtract, but there is no difference between subtraction and addition, so the result will be x squared plus 1. Then you just multiply it by x, and you will get x squared plus x, and you subtract, and you will get x plus 1, and then you just multiply by 1, x plus 1, and the result is 0. So this is your Q2, and this is your R2. So as you can see, in this case, the GCD is x plus 1, and it's presented in the form f minus g, and that's it. So your u is 1, your v is minus 1, and we're done. Okay, let's try to factorize some polynomials, but before doing that, I want to, by the way, are there any questions? So in general, oh, by the way, I need to make one additional remark. What would happen if we have this? For example, if I take Z3 x. I could take something like x to the power of 3 plus x plus 1, or something like that, and g to be 2x squared plus 1. What would you do in this case?
Divide g by 2. So
Yeah.
multiply it by 2 inverse, both.
Yes, exactly. You're right. So here, so the most confusing part is that g is not monic polynomial. Its leading coefficient is not 1. So it's more convenient to deal with monic polynomials. So before doing anything else, you just make the polynomial monic. So how do you do that? You multiply by 2 inverse. But what is 2 inverse in Z3?
2?
Yes, exactly, because 2 is actually minus 1. So you should multiply minus 1 by minus 1 to get 1. So if you multiply it by 2, so you just replace g by 2g, which is x squared plus 2. And actually, when you do some computation, it's easier to deal with minus 1 instead of 2. So you just write this as x squared minus 1, and it's easier to deal with this polynomial instead of this one. I mean, it's exactly the same thing, but technically it's easier to deal with smaller numbers, but probably negative ones. Okay. Yeah, that's an important remark, how to simplify the computation if your polynomials are not monic. And if f were monic, you would multiply by the inverse coefficient 2. Okay, so let's go to the next problem. Okay, so suppose f is a field and f is a polynomial. So if a is an element of f such that f of a equals 0, we say that a is a root. Well, I believe all of you knows the definition, but just in case, I just want to pronounce it explicitly here. So now I want to discuss some situations where it's easy to check if a polynomial is irreducible or not. Because in general, it's a very hard task to check if a polynomial is irreducible. Well, for example, for the field Q, it's almost impossible. Well, I mean, there is an algorithm, but you will die earlier than the algorithm stops his work. So in case of some specific fields, there are some algorithms that can check if a polynomial is irreducible or not. But in general, this is a very hard task. But suppose our polynomial has degree 3 or smaller. Then the claim is f is irreducible if and only if f has no roots in f. So yeah, irreducible in f of x. It's important to specify where it's irreducible, because a polynomial may be irreducible as a polynomial with real coefficients, but it becomes reducible as a polynomial with complex coefficients. So it's important to specify the field here in the claim. So how do you think why this is true?
Well, it looks like the same as in the reals.
Okay, let me show you. Well,
oh, maybe it's, oh yeah, it's kind of obvious.
Well, and actually I have to say it like this. The degree is 2 or 3, because, but before discussing this, suppose that the degree of f is 1, then what does it mean? It means that f is equal to a plus bx, and b is not 0. Well, it's clear that all these polynomials are irreducible. The polynomials of degree 1 are all irreducible. Well, why? Because you cannot present this polynomial as a product of two polynomials of strictly smaller degree. because the polynomials of strictly smaller degree are the polynomials of degree 0 or minus infinity. And if you multiply two polynomials of degree 0, well, the result will be polynomial of degree 0. So you cannot present this polynomial as a product of two polynomials of strictly smaller degree. So this is a trivial case I almost forgot to mention. So, and by the way, usually when you want to discuss irreducible polynomials, it makes sense to divide by the leading coefficient and discuss only monic irreducible polynomials. So in this case, all monic irreducible polynomials are the polynomials of this form, where lambda is an element of f. So they are all described by elements of the field. So these are monic irreducible polynomials for every field f. Now, let's prove the claim. So what does it mean? Well, suppose that the degree of f is 2. What does it mean that f is reducible? Suppose f is reducible. It means that you can present f as a product of two polynomials. Then f is a product of g and h, and the degree of g is strictly smaller than the degree of f. And the degree of h is strictly smaller than the degree of f. But f has the degree 2. The only case which is possible here is that the degree of g is 1, the degree of h is also 1, which means that f of x is the product of two linear polynomials. Well, let's stick to the case of monic polynomials. It doesn't matter, but you may add a non-zero coefficient before x. It doesn't matter. I help you understand why. If not, then I'll switch back to non-monic case. But now, this simply means that the numbers a and b are roots. So this is a contradiction. So if your polynomial of degree 2 doesn't have a root, then it's irreducible. Are there any questions regarding this proof?
One more time, I don't get the contradiction.
Oh, okay. So what do we have? Suppose that, well, just in case, if you have a root, then you're reducible. Okay. So we're proving from the left to the from the right to the left. If it has no roots, then it's irreducible. So this is the implication in this direction. So f has no roots. We want to prove that it's irreducible. Now we assume that f is reducible, and we get that it has a root. For example, here we have two roots, a and b.
I mean, it is true in general case for any degree higher than 1. Yeah?
No, it's not true in general case. It's true only for the degree 2 and 3, and you will see the counterexample for the degree 4.
Interesting. Okay.
So now, and just in case, if f is irreducible, well, it has no roots. It should be clear. Why? Because suppose that f has a root, so a is a root. So this implication holds for any degree. It doesn't matter. This one holds. But
Okay. No, makes sense.
this one. So yeah, and here you can divide f of x by the polynomial x minus a, and you will get this plus r, and r is a polynomial of degree strictly smaller than the degree of x minus a, which is 1. So r is a constant. But now, if you substitute here x to be a, then f of a is 0, because we assume that a is a root. But on the other hand, it equals r, because the first summand is 0, x minus a goes to 0. So in this case, we prove that r is equal to 0, which means that f of x is a product of q of x and x minus a. And you see this means that f is reducible. It presented as a product of two polynomials of degree strictly smaller than f. And yeah, and here we assume that the degree of f is at least 2. So in this case, it works for any degree strictly larger than 1, because all polynomials of degree 1 are reducible. Okay, so, but we discussed only the case of degree 2. What happens if f has degree 3? Well, this implication, here nothing changed. It holds for degree 3, but what happens for the opposite one? Suppose that f has no roots and we want to prove that f is irreducible. So we know that f has no roots and we want to prove that f is irreducible. Well, again, suppose that f is reducible. So the degree of g is strictly smaller than the degree of f, which is 3. And the degree of h is strictly smaller than the degree of a, which is 3. Well, there are two options. Either the degree of g is 1 and the degree of h is 2, or the other way around. The degree of g is 2 and the degree of h is 1. Well, we may change the notation and we may assume that g has degree 1. Sorry, I could denote it by like that. So here we have degree 1 and here we have degree 2. But this simply means that f of x equals x minus a times h of x, where h of x is some square polynomial. And as you can see, this implies that f has a root. I mean, a is the root, which is a contradiction again. So this explains that if you want to find a polynomial of degree 2 and 3 and you want to check that it's irreducible, you just need to check that it has no roots. It's simple to check that some polynomial has no roots because you just substitute all possible values from the field and you check that the result is non-zero. It's much simpler than factorize a polynomial f into a product of other polynomials. So are there any questions regarding this claim? Okay, let's see how it works. So let's see an example. Well, let's take our field to be Z2. So we will be dealing with Z2x. And our polynomial is x4 plus x3 plus x plus 1. Let's try to decompose this polynomial into a product of irreducible polynomials. How could we do that? Are there any ideas? I want to decompose it into a product of irreducible.
X cubed plus 1 multiplied by x plus 1, which is x plus 1 squared multiplied by x squared plus x plus 1. Okay,
you see, when you're young and your brain can find very subtle details of an example, you can simply find a trick and it saves you. Yeah, what you see here, you can, first of all, you can decompose this into a product x plus 1 times x cubed plus 1. I'm sorry.
X cubed plus 2, I believe.
X cubed plus.
No, it's okay. It's okay.
No, it's okay. X cubed plus 1. Yeah, there is no 2. Okay, but how could we possibly find such a factor like x plus 1? There is a simple method. When you need to factorize a polynomial, first of all, try to find the roots of the polynomial. So there are only two elements in our field, which are 0 and 1. Okay? Now, if we compute f of 0, the result is 1. And if we compute f of 1, then you have 1 plus 1 plus 1 plus 1 plus 1, which is 4, and 4 is equal to 0 in Z2. So this means that 1 is the root of this polynomial. So it must be divisible by x plus 1. So x plus 1 divides f. Well, x plus 1 or x minus 1 doesn't matter here for this field. So we could divide f by x plus 1 with a remainder, and we will factorize this polynomial out. So so now we know that this one is irreducible because it's linear. Now, is this polynomial irreducible or not?
It is reducible?
It's reducible.
Sure.
Yeah, why?
Because we can, I don't know, take from it x plus 1 again.
Okay, yeah, you're right, but let me formulate this in a slightly different way. It's a polynomial of degree 3, so it's irreducible if and only if it has no roots. Let's check whether it has a root or not. Well, if you substitute 0, the result is 1. If you substitute 1, the result is 2, which is 0. So again, 1 is a root. So we can divide it by x plus 1, and the result will be x cubed plus 1 equals x plus 1 times x squared plus x plus 1. Okay. And we know that this polynomial is irreducible. And what about this one?
It is irreducible.
And why?
Because it has no roots.
Yes, exactly. So you substitute 0 or 1, the result will be 1, so it's irreducible. It's irreducible because it has no roots. And its degree is 2. So now we see that the complete factorization for the initial polynomial f is this x plus 1 square, x squared plus x plus 1. Okay. You can apply exactly the same method for any polynomial of smaller degree. Well, if you have a polynomial of degree 3, well, it's easy to recognize an irreducible polynomial because of this criterion. But in case of polynomial of degree 4, if you consider x squared plus x plus 1 squared, this polynomial is reducible, but it has no root. You see? It's a product of two irreducible polynomials of degree 2. So if you substitute 0 or 1, the result will be 1. But it's clearly a product of two square polynomials, and G is a polynomial of degree 4. So this is an example showing that this criterion works only for the polynomials of degree 2 and 3, and for polynomials of degree 4, it doesn't work. And actually for any larger degree, it doesn't work. Well, it works sometimes, like for the real numbers, all negative degrees implies that you have a root, but in general, it doesn't work. Okay. The next thing I would like to discuss is how to find irreducible polynomials over field Z2. It's a very important task to solve. So let me show you how to do this. So in general, the problem is this. So you have Z2 or any other field like Z3, Z5, but I just want to demonstrate it in case of a smaller field because it's easier to compute. And we want to find a reducible polynomial, say, of degree 4. How would we do that? Well, first of all, you should know the answer. For any degree, you can find a reducible polynomial of this particular degree. It works for any field ZP. So if you consider this field, then for any n, there is a polynomial f in ZPX such that the degree of f is equal to n and f is irreducible. So it's always possible to find an irreducible polynomial of a given degree, but it's hard to find one. So how could you do that? Well, there is one way of doing it, and you can do it dynamically. So you just compute all the polynomials of degree 1, all the polynomials of degree 2, all the polynomials of degree 3, all the polynomials of degree 4. And so you list them, and you can find all the reducible going from the left to right. Let me show you how it works. Well, what are the polynomials of degree 1? These are just x and x plus 1. And that's it. There are no other polynomials.
Are we working with Z2?
Yeah, we're working with Z2, this particular example. So now, what are the polynomials of degree 2? It's x squared plus, and here we have to write all possible options for other terms. So you have, so let me write it here. You have x squared plus ax plus b, where a and b go through all the elements of Z2. So there are 4 options. Plus 1, x squared plus x, and x squared plus x plus 1. Now, how do you recognize irreducible polynomials? There are 2 possible options. In case of degree 2 and 3, we have this powerful tool. It's enough to check that the polynomial has no roots. So we just substitute 0 and 1 and see what is the result. X squared gives 0 if you substitute 0. X squared plus x also gives 0 if you substitute 0 or 1. And if you substitute 1, x squared plus 1 gives you 0. So the only option here is this. So in degree 1, you have 2 irreducible polynomials. In degree 2, you have only 1 irreducible polynomial for Z2. So this is the first way how to check which one is irreducible. The second option is this one. We know that this polynomial must be a product of the polynomials of the smaller degree. So you just multiply all possible polynomials of the smaller degree with themselves, and you get these options. So x times x gives you x squared, x plus 1 times x plus 1 gives you x squared plus 1, and x times x plus 1 gives you x squared plus x. So this one is out of range. So this one is irreducible. So it's not presentable as a product of polynomials of smaller degree. Now we have to do exactly the same for the degree 3. Well, here, how many polynomials do we have here in degree 3? Not necessarily reducible, just how many polynomials of degree 3? Again?
Maybe 8.
8, exactly. So let me write them down. So x cubed, x cubed, x cubed, x cubed. And here we write plus 1 plus x plus 1. And then we just add x squared to everything. x cubed, x cubed, x cubed, x cubed, plus x squared, plus x squared, plus x squared, plus x squared, and then plus 1, plus x, plus x, plus 1. So these are all possible options. Now, so again, since this is a polynomial of degree 3, it's irreducible if and only if it has no roots. Let's check all the polynomials with roots. So if you substitute 0, then this guy goes to 0, this guy goes to 0, this guy goes to 0, and this guy goes to 0. If we substitute 1, then the polynomials with even number of terms give you 0. So this one give you 0, and the last one give you 0. So in this case, these two polynomials are irreducible. So we have two polynomials of degree 3. Okay. Now, how do you compute reducible polynomials for degree 4? Well, you have to repeat exactly the same procedure. But let's try to compute the amount of reducible polynomials of degree 4 instead of computing exactly how the polynomials look like. So suppose we want to,
there will be like 16 polynomials in total, and we need to somehow find how many combinations we have, how many pairs we have.
yeah, you just list all of them, and you want to compute the amount of reducible ones. So there are exactly 16 polynomials. So let's try to compute the reducible ones. And here we use the fact that the polynomial ring is a unique factorization domain. So every polynomial is uniquely presented as a product of irreducible ones, well, up to some invertible coefficients. So let me show you. Well, suppose that f is a polynomial of degree 4. I will write the index 4 here.
Maybe it's like binomial coefficient plus n.
So yeah, it must be a coefficient times, for example, some p1 to the k1 and so on, ps to the ks. This is the general claim, yep? Where pi are irreducible and pi are irreducible and the degree pi are irreducible and the degree of pi is strictly smaller than the degree of f. But in our case, we already found all the reducible polynomials of degree smaller than 4. These are polynomial, these two, these one, and these two. You see? So we already know all possible choices for P1 and PS. But what are the options for the element A? Well, in Z2, we have only two elements, 0 and 1, and A must be a non-zero element, so A is always 1. So we just want to decompose a polynomial of degree 4 into a product of the polynomials marked by the blue lines here. Let me show you the options. The option number 1, F4, is a product of 4 polynomials of degree 1. I will write it like this. The polynomial 1 of degree 1, the polynomial 2, a polynomial 2 of degree 1, a polynomial 3 of degree 1, a polynomial 4 of degree 1. So we need to compute all these how many options we have here. The second option, when we have 2 polynomials of degree 1 and 1 polynomial of degree 2. The next option, we have 2 polynomials of degree 2. And the other option,
You wrote 1, 2. It should be 2, 2.
Oh, yeah, you're right. It should be 2 here and 1, 2 here. So these are all possible options. So we decompose into 4 linear factors, 2 linear, 1 square factor, 2 square factors, 1 linear, and 1 cubic. and these are all the options, okay? Now we need to compute, by the way, because of the uniqueness of this decomposition, all the polynomials we get here and the polynomials we get here are distinct. So we just need to compute the amount of these ones, the amount of these ones, the amount of these ones, and the amount of these ones, add them all together, and this will be the amount of all reducible polynomials of degree 4. Are there any questions?
No.
Okay, do you know how to compute how many polynomials are presented in this form? That's a discrete math problem.
Yeah, it's kind of stars and bars problem, like.
Yeah, exactly. So, so now, how many options do we have for the polynomial of degree 1? We have x and x plus 1. Now, we have 4 positions, which is here. We have
So
4
16.
options, and we have 2 classes, so we need to add 1 divider somehow. So we have 5 elements, square, square, line, square, square, and we have to choose 1 position out of 5 for this divider. So there are C5, 1 elements, or in other notation, 1 choose 5. 5 choose 1. So how many options do we have? And the number is 5. Yep. Now, how many options do we have here? So for this guy, we have only 1 option because we have only 1. I wrote 2, but it's clearly 1. We have only 1 irreducible polynomial of degree 2. And here we solve the same problem, but with 2 polynomials instead of 4. So it will be 3 choose 1 times 1, which is 3. So here we have 5. Here we have 3. Now, what do we have here? We have only 1 polynomial of degree 2, so the only option for each factor is the only reducible polynomial of degree 2, so there is only 1 product.
Excuse me, and is each of these P and Q irreducible?
Yeah, I mean, in this notation, each of these polynomials is irreducible.
Oh, okay.
Because otherwise it's pointless. Okay, so and in the last case, we have 2 options for this guy and 2 options for this guy, as I remember, if I remember correct. Yes. So there are 2 times 2 options, which is 4. And now, how many cases do we have? We have 13 reducible polynomials. So there are 13 reducible polynomials. So hence, we have 3 irreducible polynomials here and 13 reducible ones. Well, it's actually not hard to compute explicitly the irreducible polynomials here, but well, somehow it's hard to do on a whiteboard, but I did this on a sheet of paper. It doesn't take a lot of time. And actually you can compute by the same, using the same technique, the amount of irreducible polynomials of degree 5. So you see, you don't need to know how these polynomials look like. You just need to know how many polynomials you have here. You know that you have 3 irreducible polynomials. Then, if you want to compute all the irreducible polynomials of degree 5, you just compute the amount of all polynomials of degree 5. You'll get 32 polynomials. And then, following the same technique, you just count all, well, you just list all possible factorizations for your polynomial into irreducible ones of different degrees. And then you count the amount of these factorizations, and this will give you all possible reducible polynomials. Okay, now, well, let me show you what's going on here. So we were computing irreducible polynomials over Z2 for small degrees like 1, 2, 3, and 4. So you do it going from the smaller degrees to the larger degrees. For the degree 2 and 3, irreducibility is equivalent for having no roots. And well, going further requires some computational skills, but it's still possible. And if you just need to compute the amount of polynomials, you don't need to compute them. You can compute just the numbers. And there are like general rules for computing the number of irreducible polynomials. They're called Möbius rules, probably. I don't remember exactly. So the number theory has all the answers. Okay, are there any questions regarding this? Okay, if there are no questions, let me switch to a different problem. I want to discuss homomorphisms. So we have this ring, f of x quotient by f. And I want to compute homomorphisms from this ring to a different ring. So this is the general problem. So, but let me formulate it more precisely. So I will assume that F is a field, R is a ring, and R contains F as a subfield, as a subring. So this is my setting. Now, F, I'll take a non-zero polynomial. And then, then I want to describe all possible homomorphisms from this ring to R, but with an additional condition. I want this homomorphism to take elements of the field F to exactly the same elements of the field F inside R. I want F of A to be A for any element of the field. So I want it to be identical on the field F. So this is what I want to explain. So again, so F is a field, R is a ring containing our field as a subring, and I want to describe all possible homomorphisms from this ring to R such that this homomorphism acts trivially on all their coefficients. So this is the goal. So now let me formulate the, but just in case, are there any questions regarding the problem, regarding the state? Is it clear what are we going to do or not? Okay, now what is the answer? The answer is the following. You should take all possible elements R such that they are roots of the polynomial, but this means the root, oh, accidentally, they are roots in R. So I solve this equation in this ring, and I find all possible roots. And then for each element R, I can define a homomorphism by the following rule. Element G goes to G of R. And this defines a homomorphism phi of R. So it's just a substitution of a root of a polynomial F. So again,
Application, yep. Or that's an equivalence.
Again?
logically, is it an implication or an equivalence?
It's an implication. So each homomorphism is of this form, like uniquely. So there is a bijection between homomorphisms of rings such that f of a equals a for all elements in F is in one-to-one correspondence with the element R in R, such that f of R equals 0 in R.
Okay, thanks.
Yeah. So so phi of R corresponds to R here. So this is the complete description. All possible homomorphisms are in this form, and moreover, different elements R give you different homomorphisms. So this is how it works. So for example, if you want to, well, I'm not sure that it's a good idea to explain the reason for that. Simply you just need to check that the map is a well-defined homomorphism. But okay, let me say a couple of words regarding why this is true. Well, you see, suppose you have a homomorphism from this ring to some other ring. Then, if you take an arbitrary element here, j of x, it's of the form a0 plus a1x plus and so on, an minus 1 x to the n minus 1, where the degree of f is n. Okay? Then when you apply a homomorphism phi to the element g, phi of g equals phi of a0 plus a1x plus and so on plus an minus 1 x to the n minus 1. Okay? But since phi is a homomorphism, then it will be phi of a0 plus phi of a1 phi of x. It preserves multiplication and addition plus and so on phi of an minus 1 phi of x to the n minus 1. But then we have this additional assumption that if you apply phi to the elements of F, they stay the same. So all the coefficients will be exactly the same. So the result will be a0 plus a1 phi of x plus and so on plus an minus 1 phi of x to the n minus 1. Now, let me denote phi of x by r. Then what's written here is j of r. So if you have a homomorphism from this ring to any other ring, obeying the rules above, then it must take any element g of this ring to g of r, where r is an image of x. That's the first observation. The second observation, f is equal to 0 in f of x quotient f, just by definition, because the remainder of f is 0. But if you apply the homomorphism, you will get phi of f equals phi of 0, which is 0. But from the other hand, we know that it must be f of r. We computed this for any g. Well, this simply means that r is the root of f in the ring R. So this means that if you are given a homomorphism, then so you just so your R is just phi of x. This is how you compute R using your homomorphism. You just apply phi to the element x. So this is just the image of the element x inside R. So it's precisely a root of the polynomial f. So this gives you a map from the left-hand side to the right-hand side. in order to show that every element gives you a homomorphism, that this map is surjective, well, you just show that the formula phi of G equals G of R is a well-defined homomorphism. So it preserves addition and multiplication, and these are just simple computations, and I don't want to waste time doing that. But if you wish, I can write the proof down and upload it to the wiki page. So it just, if there is someone who is interested in the proof. So, but this just some brief explanation how you should think of this homomorphism. So every homomorphism from this ring to this ring is just a substitution instead of x of a root of the polynomial f, but the root must live in the right-hand side in the ring R. Are there any questions regarding this?
Is there any specific case when this becomes an isomorphism?
Well, yes. It may happen that this map is an isomorphism, but in this case, well, first of all, in order to be an isomorphism, you need to check that you're surjective and injective. And if you want to check that you're an isomorphism, you simply check these two properties, surjectivity and injectivity. But sometimes we may guarantee that this map is always injective. For example, if F is irreducible when this is a field, the map will be injective automatically. Okay, but let me show you several examples, okay? And you will see, for example, why in case of a field, this is an injective map. So what are the examples we may deal with? Well, an example number one, well, let's take R of x, and we will take f to be x squared plus 1. Then we have this ring R of x quotient by x squared plus 1. Explicitly, it consists of elements a plus bx, where a and b are real numbers. And the multiplication is given by this reminder formula, modular x squared plus 1. But now I can produce a homomorphism to the field of complex numbers. Well, inside the complex numbers, we have a root of the polynomial x squared plus 1. There are two elements, I and minus I. They are roots of x squared plus 1. So there are two homomorphisms from the left-hand side to the right-hand side. So a homomorphism phi I, which takes any element g to the element g of I, and a homomorphism phi minus I, which takes any g, so let's write this like here, which takes any g to g of minus I. These are all possible homomorphisms from this ring to this one. And let me show you that these homomorphisms are actually isomorphisms. Well, let me write explicitly. Well, every g is of the form a plus bx. So the first map takes it to a plus bi, and the second map takes it to a minus bi. Well, it's obviously a surjection because every element of C is of this form. So just by looking at the map, we see that this is a surjection. Now, what about injectivity? Well, you see the left-hand side is a vector space of the real numbers. It has bases 1 and x. So the left-hand side is a vector. Well, actually, well, it's here. It's you don't need even this. In this case, well, you see that every element on the left-hand side is uniquely represented in the form a plus bx, and every element on the right-hand side is uniquely represented in the form a plus bi. So it's clear that here it's a bijection. So for the first map, you just replace x by I, and in the second case, you just you replace x by I, and you replace addition by subtraction, and that's it. So in this case, it's just clear that the map from the left to the right is a bijection, just looking at the elements. Okay, so this simply explains that this is an isomorphism. Are there any questions regarding why this map is an isomorphism? Okay, and these are all possible homomorphisms. By the way, you can do exactly the same procedure with any irreducible polynomial. For example, x squared plus, say, I need a polynomial with no roots, something like this, I believe. Yeah, this one is irreducible. Okay, this one has no roots. So you may also produce two homomorphism to C star. Why? Well, because this polynomial has two complex roots. These are two complex roots of unity, xi and xi prime, such that xi cube equals 1. And you just take a plus bx to a plus b xi, or a plus bx goes to a plus b xi bar, where bar means complex conjugated number. So, and these are two possible homomorphisms from the left-hand side to the right-hand side. Well, and here, well, it's clear that this map is surjective. You can just explicitly compute this looking at the real and imaginary part of the number xi. But when you want to show that it's injective, you could do this. The left-hand side is a two-dimensional space over R. The left-hand, the right-hand, oh, I'm sorry. The left-hand side is a two-dimensional space over R. The right-hand side is also a two-dimensional space over R. And this map is a surjective linear map, but then it's automatically injective. And actually here you can even show its surjectivity without computation. For example, you will get all real numbers. So the image at least has dimension 1, and then you have at least one complex number, which is when a is 0 and b is non-zero, you have at least one complex number, and when a is non-zero and b is 0, then you have at least one real number. So the image at least two-dimensional, so you're automatically surjective. So that's how you could do that. So, and both homomorphisms are actually isomorphisms. So this guy is actually isomorphic to the field of complex numbers. Okay, are there any questions? Okay, now I want to switch to the Chinese remainder theorem and discuss one additional case. You will need it in your homework. So, for example, let's take the polynomial ring Q of x, and we have 10 minutes, as I can see. So yeah, we have enough. So let's f be, say, x squared minus 2, and g is x plus 1. Then, well, Q of x quotient by x plus 1 times x squared minus 2 is isomorphic to Q of x quotient by x squared minus 2 times Q of x quotient by x plus 1. This is the Chinese remainder theorem. So what other elements here? Well, since the polynomial on the left-hand side is a cubic polynomial, all the elements here are just polynomials of the form like this. All the polynomials of the degree not greater than 2. The elements here are the linear polynomials at least linear. And the elements here are just constants, because you just take all the polynomials modulo x plus 1, the result will be constant. The remainder will be a number. And now, how do you map? So if you take an element here, how do you map it to the right-hand side? You just take g modulo x squared minus 2, and here g modulo x plus 1. But what is g? So let's say g is this polynomial, a0 plus a1x plus a2x squared. So what is g modulo x squared minus 2? So a0 plus a1x plus a2x squared. Well, when you take it modulo x squared minus 2, it means that x squared becomes 2. So the result is a0 plus 2a2 plus a1x. This is modulo x squared minus 2. And if you want to compute this modulo x plus 1, you will get a0 plus a1x plus a2x squared. When you take it modulo x plus 1, it means you take x to the minus 1. So the result will be a0 minus a1 plus a2. This is modulo x plus 1. So when you take modulo something, you think of this something as something being 0. And if x plus 1 is 0, then x equals minus 1. So you use this trick to compute this without using explicit division with a remainder. And here, since you think of this as being 0, x squared minus 2 is 0, then x squared is 2. So you just substitute 2 instead of x squared, and you will get the result of your division with a remainder. So this is how you compute the map from the left to right. So this guy goes to a pair. The first element of the pair is this one, and the second element of the pair is this one. Are there any questions regarding this map? Okay, let me reformulate my question. Is there anyone who understands all the details here?
Yep.
Okay, that's
Yep.
cool. Nice, that's nice. Now, the interesting question, how to compute the map in the other direction. So you're given a pair of polynomials, a plus bx and some element c. So how to compute this one explicitly? And you do this in exactly the same way you did this for integer numbers. So first of all, you want to compute, okay, let me show you. So first of all, you want to compute what corresponds to polynomials of this form. So you find some polynomial, say u, and the polynomial v, and then if you have something like, say, hg here, then it goes to uh plus vg. This is how you compute the map in general. So exactly the same procedure as with integer numbers. So the only problem is how to find such polynomials u and v. Well, in this case, we represent the greatest common divisor of x squared minus 2 and x plus 1, they're co-prime, as a linear combination. So we say 1 equals, let's say, a x plus 1 plus b x squared minus 2. Here a and b are polynomials, rational polynomials. And now we see that this polynomial is equal to 0 modulo x squared minus 2, but equals 1 modulo x plus 1. So this is your v. And this polynomial is equal to 0 modulo x plus 1 and is equal to 1 modulo x squared minus 2. So this is your polynomial u. So the only problem is to compute these polynomials a and b. So that's why it's important to know how to compute this expansion of the greatest common divisor into a linear combination of the initial polynomials. So if you know how to solve this problem, you can solve this problem. So you can compute the inverse map. So then you just substitute u and v in this formula. You just substitute the coefficients for h and g into this formula, and then you just compute the result. And that's all. So this is how it works in the opposite direction. Are there any questions regarding this? Okay, well, congratulations. That's more or less everything that I wanted to explain. Well, I actually was afraid that I do not have enough stuff for the lecture, but I had to skip like 1/3 of the plans. And during the seminar, we were lucky to do everything that I wanted to. So, okay, if you have any questions, please ask. If there are no questions, then I'll see you next time, and thanks for being here with me. So I believe there is no questions. Okay, thank you guys. It's cool that you came here at this evening. Yeah, it's nice that, well, actually it's really cool that you're so interested and that you're coming here so late at evening instead of sitting with your family. Well, thanks a lot, and see you next time.
Thank you very much.
Thank you.
Bye.
Thank you.
Um,
Yeah.